Hello and welcome to our work on client obliviousness in oblivious parallel RAM. My name is Gareth Davis and this is joint work with Christian Janssen and Dan Martin. To motivate the problem tackled in our work, consider an organisation that operates in multiple countries and uses a shared database for storing files that is hosted by a cloud storage provider. This organisation, and thus these geographically disparate clients, do not trust their CSP and so use symmetric encryption before uploading any data. Further, the database content is sensitive and so the clients want to hide their access patterns from the server. This is achievable using oblivious RAM, or since there are multiple clients, the clients deploy its parallel cousin OPRAM. However, most OPRAM schemes have communication-heavy protocols that transmit read and write requests among the clients. This may not be desirable in the presence of modern data legislation, and it may be necessary for certain data to physically stay within a geographic region such as the European Union. Until now, it has not been clear how to achieve this, or even to formally model this security requirement. In our work, we demonstrate a new property for OPRAM schemes, which we call client-obliviousness, that captures this problem and show how it can be achieved. We first describe oblivious RAM and oblivious parallel RAM in the context of outsourced storage, and introduced important prior constructions. Then we describe client obliviousness and show how to achieve it. Oblivious RAM has been a rich research area in the last 30 or more years since the seminal works of Goldreich and Ostrowski. The idea is that some client that makes read and write requests to some untrusted memory can do so in such a way that even the access pattern is hidden. Each request consists of read or write, a block identifier, and in the case of a write, the new data to be placed in that block. If a user stores n data blocks in some memory, an ORAM compiler turns a sequence of access requests into a new sequence that is independent of the original sequence by randomly permuting real and dummy accesses and reshuffling memory entries. The property of obliviousness from an eavesdropping adversary that sees all ciphertexts in the database is modelled formally as an indistinguishability game. We now describe PathORAM, perhaps the best known ORAM scheme, that was introduced in 2013. The database or memory is represented in a binary tree, with the tree nodes each storing a fixed number of data blocks. The protocol is very easy to understand and has been implemented in many different use cases. This makes parameter selection more straightforward than for some other schemes. A client stores n data items in a binary tree, where each node is a bucket that contains a fixed, constant number of blocks, which in this example is 3, and each block is, say, 4 kilobytes and consists of the block ID and data, all encrypted under a key known only to the client. For each unused block in a bucket, a dummy block is placed, so each node is actually filled with 3 blocks, but on the slide we only indicate the real blocks. The client stores locally a position map that details on which path each block is stored. This is given by a tree leaf. We underline the block identifier throughout the rest of this talk. The client also stores a stash, which contains blocks that it was not possible to place back in the previous access. So block ID 2 has position 8, which means that it is stored somewhere on the path from the root node to leaf 8, or in the stash. To modify block 2, the client first picks a new leaf location for block 2, in this case 11. Then the client reads the entire path from the root to leaf 8 and places these blocks in the stash. The client finds block 2 amongst these data blocks and replaces the data with its desired value. Then the client writes back the data along each path, taking into account the position of each block and pushing each block as far down the tree as possible along these 2 paths. The block that was originally in the stash had position 9, so can now be placed in the tree, and one of the blocks that was in the root node has position 15, so can now be moved down 1 level. The server only sees encrypted buckets, so it only sees a portion of the tree buckets being accessed. In oblivious parallel RAM, M clients share the database, and in each time step the clients make 1 or 0 accesses. These are processed and executed in one go. Boyle, Chung, and Pass gave a definition of the primitive and a construction. An important observation is that their system setting was for CPUs to be executing parallel programs on the same local memory, so they did not focus on optimizing inter-client communication or consider trust between the clients. Other primitives exist that consider multiple users with their own ORAM, where clients enable access to parts of their own storage. We stress that in OPRAM, all locations are available to and owned by all of the clients. Here we describe the generic method for developing an OPRAM compiler for a given round of the protocol. Assume from here on that all M clients make an access. In the BCP paper, they describe how to deal with fewer clients accessing. Further, assume some tree structure for the database, as we saw before. The M clients provide to the compiler their accesses. However, if two or more clients wish to read the same position, then reading that position just once will trivially leak how many collisions have occurred. Further, if two or more clients wish to write, then the protocol needs to decide which client gets priority. In all prior worked hours, the clients are labeled, and so the lowest identifier gets to write. An oblivious aggregation phase is required to deal with these issues to ensure that the compiler eventually specifies M accesses to M different positions. We will explain this step in more detail later on in the context of our construction. Even after this step, it is not yet clear which clients should proceed to make these requests, so an oblivious election phase assigns accesses to clients. The parallel reads can then occur. Note that if a client wants to write, then it always additionally receives as a read the data that was previously in the location that it requested. Then, the designated reading clients must transmit these data blocks to the clients that requested them. Now it is time to prepare the write-back procedure. In tree-based schemes, it is generally the case that the new position for a data item after it is accessed is just random selection from the memory space, and this information, i.e. the new position and the data to be written, must be given to clients to make this write-back. Then the data is written back and flushed to ensure that the client stashes do not overflow. The Subtree OPRAM scheme of Chen, Lin, and Tesoro is a generalization of PathORAM to M parallel accesses. They observed that for parallel accesses, flushing one path at a time is unnecessary, and so their parallel flushing procedure is a considerable improvement over the trivial generalization of PathORAM. Their crucial observation is that each of the accessing clients can be responsible for making accesses to one section of the partition database. To do this, the top log M layers of the tree are removed, and each client maintains one subtree plus their own stash. The position map needs to reflect this partitioning approach. In our example from earlier, we have multiple clients in different legal jurisdictions, which may invoke different requirements for which data can be stored where. This in itself is a reason to reduce the data that is transmitted between the clients in the execution of the protocol. For the rest of this talk, we assume the existence of a routing entity that sanitizes accesses and produces the dummy reads discussed earlier in the event of access collisions. In many of the motivating scenarios for OPRAM, there will be one organization with multiple client devices accessing the shared database, and so the router could just be a central system administrator. In some applications, this router could also enforce a data protection policy, for example, keeping some data in a certain subset of the partitions. Given this system setup, we observe that some information is inherently leaked in any OPRAM protocol. In particular, clients have to read data blocks and write them back to new positions. Given this, we aim to hide as much as we can. So from the perspective of a client participating in the protocol, for any access made by another client, it should not be possible to infer who made the initial request or which positions outside of that client's storage zone or partition are being read. We follow the cryptography literature in capturing the property of client-obliviousness via a game that is played between an adversary and a challenger. The adversary A provides three initial values. M is the number of clients, T is the number of rounds, and a corruption strategy. This strategy indicates, for each client, either a round number or perp. The adversary then corrupts that client from that round onwards. In the example, the adversary corrupts the first client from round 3 onwards, does not corrupt the second client, and corrupts the mth client from round 17 onwards. The challenger then generates a sequence of accesses for m clients in t rounds and applies the compiler. In each round, A sees the decrypted transcript for its corrupted clients. Eventually, A outputs a client identifier, ID, a block identifier, A, and a round number, and wins if an access to that block occurred. In the full version of our paper, we describe a number of potential extensions to this experiment. We give a proof of concept instantiation of an OPRAM compiler that achieves client obliviousness. Our construction functionally emulates the Subtree OPRAM protocol of Chen et al., yet we need to replace all of the vulnerable subprotocols to minimize the plaintext data transmitted between the clients. In this talk, we detail the first 2 steps of our protocol that replace the oblivious aggregation and oblivious election protocols used in Subtree OPRAM. However, there are a number of other subtleties that we omit here, and you can find these in our paper. Our construction uses existing and efficient primitives. In the first step, the clients anonymize themselves from the routing entity R. Each client prepares its access, where ACK here means an encoding of this information. OP is either read or write, A is the block identifier in the database, and in the event of an operation being a write, data is some string of appropriate length. The client chooses a one-time key K and a pseudonym that will be used to hide the client's identity from the router, then encrypts this information under the router's public key. This will be the final step in an onion encryption, and so the client chooses 3 onion nodes. For ease of understanding, just think of the clients forming an onion network amongst themselves. However, this could be any onion network. Then the client prepares the onion ciphertext and passes it through the onion network such that it will eventually reach the router. As all M clients follow this procedure, the router receives M ciphertexts, which it then decrypts. Now the router will process these requests and pass the appropriate information to the partition owner. The router has write access to the position and partition map, while the clients only need read access to the subset of the partition map referring to that client's partition. If any of the pseudonyms collide, then the router aborts and restarts the protocol. The router must now deal with colliding requests, i.e. multiple clients accessing the same position, and implement some policy that defines what happens if 2 clients wish to write to the same position. In the event of any collision, read or write, the router must produce a fake read that eventually no clients will receive. Now that the router has M requests to unique block positions, it must choose new positions for these blocks for subsequent rounds and update the position map. For each request, the router fills out a vector of one-time keys. S of these keys are real, i.e. S clients wanted to access this position, and M minus S are fake. Once the client making the read looks in the position map, the new position will already be written there, so the client needs to know the old leaf, denoted LO, in order to find the block. Once that data block has been recovered, the reading client will need to transmit that data to all who requested it, hence the vector of one-time keys, and also needs to transmit to the new partition owner of the block what data needs to be written. Note that this is the real identity of the partition owner, and this is independent of the pseudonyms used for anonymization. If the request being made was a read and thus no new data is being written, a special string indicating this, denoted by data perp, will be placed in the data field. The router does this for each request and groups these requests based on the partition owner of the block location that existed prior to the position map being updated. These request information values are then sent to the partition owners using public key encryption. Note that on average, each client will have 1 access in that partition, but of course they could have 0 or many. For each of the request information values that a client receives, where here we declutter the notation from the previous slide, the client reads the path to the old leaf and finds the appropriate block, then encrypts this block with each of the one-time keys in the key vector. We stress here that this client does not know which of these keys are real and which are fake, so it does not know how many clients, if any, actually requested this block. The client then sends this ciphertext vector to all other clients who will use trial decryption until they receive a valid representation of the block that they accessed. Next, it prepares the value data, which was either specified previously or in the event that a read occurred, data is whatever data is already in the block. The value IDN, which specifies the identity of the partition owner for writing back this block to the database, is then used to create one value ciphertext CTJ and m-2 fake ciphertexts, which are just encryptions of a fixed length string. One ciphertext is then sent to each of the other clients, such that the genuine partition owners can write back correctly. The protocol then follows the subtree flushing procedure of Subtree OPRAM. In our paper, we present a formal definition of client-obliviousness, which is a new property for OPRAM schemes that captures the data transmitted between the clients. We then give a proof of concept construction that achieves client-obliviousness that is inspired by Subtree OPRAM. A number of open problems remain in this domain, and we mention just a few here. In our construction, the partitions are fixed for the entirety of the scheme, yet it may be desirable to allocate partitions dynamically. Our construction assumes that the adversarial clients and the router are honest but curious, and extending this to malicious security, where the clients can deviate from the protocol, appears to be a considerable challenge. Finally, our construction is a proof of concept, and so it is not optimized, and many of the phases require m or even m² messages to be sent. Is it possible to do any of these subprotocols in a more efficient manner? Thanks for listening, and please check out the full version of our paper for further details.